So last time we have studied limit superior, limit inferior of a sequence and relation between limit superior, limit inferior and limit of a sequence. If for a convergent sequence all the three are the same. So we are considering the convergence of sequence. If sequence has limit L, fixed limit L, then the sequence is said to be convergent. But there are different criteria to decide the sequence is convergent or not. One of that we have studied earlier is if a sequence is monotonic and bounded, then it is convergent. Now we shall consider another criteria for convergence, which is known as Cauchy sequence. Cauchy is a name of mathematician, and the criteria, if the sequence is Cauchy sequence, then it will be convergent. So we first define what is Cauchy sequence. The definition for Cauchy sequence is a sequence Sn of real numbers is said to be a Cauchy sequence. If for given or any epsilon greater than 0, there exists n. As earlier, n is positive integer, n belongs to I, such that absolute difference of Sm and Sn is less than epsilon, and this is for mn greater than or equal to n. Now this is the definition of Cauchy sequence. For given for any epsilon or given epsilon greater than 0, there exists capital N belongs to I, such that absolute difference of Sm and Sn. That means mth term of the sequence and nth term of the sequence. The difference between mth term and nth term of the sequence is less than epsilon, and this happens after capital N terms. N both are greater than or equal to n. Then the sequence is said to be a Cauchy sequence. The meaning roughly is, as the terms go on increasing, the distance between the terms become less and less, or the terms becomes closer and closer when n becomes larger and larger. That is the meaning of Cauchy sequence. For example, if you consider this sequence 1 by n, then the terms are like this: 1, 1 by 2, etc. We know it. And the distance difference between first term and the second term is 1 by 2. But if you consider the 100th term and 110th term or 1000th term, then the difference between these terms is becoming less. So these terms are closer, more closer than these two terms. The distance between these two is 1/2, but the distance between these two terms, this is 0.01 and this is 0.001, that distance is less than half. So that means as n becomes large and large, the terms becomes closer and closer, and the meaning is the distance between or difference between mth term and nth term is less than epsilon. So this is about the definition of Cauchy sequence. Now we shall consider the relation between convergent sequence and Cauchy sequence. The first result is as a theorem. If Sn is a convergent sequence, then Sn is a Cauchy sequence. That we shall consider. So if a sequence of real numbers is convergent, a sequence Sn of real numbers converges, then Sn is Cauchy. or Sn is Cauchy sequence. Now to prove this result, see if it is convergent, then it is Cauchy. Convergent implies Cauchy. So the converse part also we shall prove, but here the sequence converges means it has a fixed limit, and let L be the limit of the sequence. And then we have to prove the sequence is Cauchy, means this condition is to be satisfied. So the proof of this theorem is, we shall consider the sequence converges, so therefore we shall assume L be the limit of this sequence. Let limit n tends to infinity of Sn is equal to L, and we apply the definition of limit of sequence. So therefore, given epsilon greater than 0, there exists n belongs to I such that absolute difference of this term of sequence and L, such that mod of, instead of n we use k later, because n are used in the definition of Cauchy sequence. So we can consider Sk minus L is less than epsilon for k greater than or equal to n. So this we shall consider. And again, instead of epsilon, we may consider epsilon by 2. Epsilon can be taken at our choice. So we can take epsilon as 1.1 or epsilon instead of epsilon by 2. Epsilon is greater than 0, epsilon by 2 is also greater than 0. So we have taken purposefully epsilon by 2, and instead of n we have written k. Now we shall suppose mn greater than or equal to this capital N. For small n greater than or equal to n, we have mod of Sm minus Sn, and this we shall write as, we want to show this is less than epsilon, and therefore we have considered this expression Sm minus Sn. This is equal to Sm minus L plus L minus Sn, absolute value of this, and we have subtracted and added L, so the term remains the same. And we use the property of absolute value function. Mod of a plus b is less than or equal to mod of a plus mod of b, and therefore this is less than or equal to mod Sm minus L plus mod of L minus Sn is same as Sn minus L. It is absolute difference, so mod of a minus b is same as mod of b minus a. And we see this mod of Sm minus L. This is n both are greater than or equal to n, and therefore if a term is greater than this capital N, it satisfies this condition. So therefore Sm minus L will be less than epsilon by 2, because m is greater than n. So therefore this is less than epsilon, and also for the second Sn minus L, that also satisfies this condition, or we may refer this as 1, and this is strictly less than epsilon by 2 first term, plus this also satisfies this, because n is greater than n, capital N, and if all the terms which are greater than or equal to capital N satisfies this condition, the difference between that term and L is less than epsilon by 2. So therefore both these terms will satisfy this condition 1, epsilon by 2 plus epsilon by 2, and which is epsilon. So this is by 1, and thus or therefore what we have is the difference Sm minus Sn, absolute difference of mth term and nth term, is less than epsilon, and this is true for mn greater than or equal to n, capital N. And see, this is the exact definition of Cauchy sequence. The difference between mth term and nth term is less than epsilon, and hence Sn is Cauchy sequence. And this proves the theorem. So we have proved the result. Now we shall consider the second result as a lemma. We also want to prove a converse of this result. Means if the sequence is Cauchy sequence, then the sequence is convergent. That we want to prove. And to prove that result, we shall prove first a lemma. And the lemma is, if Sn is a Cauchy sequence, then Sn is bounded. If Sn is a Cauchy sequence, then Sn is bounded. A Cauchy sequence is bounded sequence. That we have to prove. Now the proof for this lemma. Let Sn be a Cauchy sequence. And now we shall apply the definition. If Sn is Cauchy sequence, then what we must have? Given epsilon greater than 0, there exists n satisfying this condition. Given epsilon, given it may be greater than 0, any value, and therefore here we can consider, therefore given epsilon, we take epsilon as 1, because 1 is greater than 0. So therefore we can take epsilon as 1. There exists capital N belongs to I, such that this difference Sm minus Sn is less than, epsilon is 1. We have taken epsilon as 1. So less than 1 for the same condition Mn greater than or equal to capital N. Now what we shall consider is, we shall take this n as fixed, and we can write it Sm minus S capital N in particular, or therefore mod of Sn minus S capital N is less than epsilon, less than 1, epsilon is 1 for, now because we have fixed this, here we may write only m greater than or equal to n, capital N. Now see what we have done. This is true for mn either greater or equal to n. We have selected this small n as capital N, and therefore this term becomes S capital N. And only that now the term is fixed. Now only varying term is Sm. So Sm minus S capital N is less than 1, and there is no need to write condition for n, because n is taken as capital N, m greater than or equal to n. So this is the relation we have. Now what about mod Sm? Mod Sm we can write as absolute value of Sm. We write as Sm minus Sn plus Sn. Subtracted and added Sn. And now we use again the absolute value property. So this will be less than or equal to mod of Sm minus Sn plus mod of Sn. And you see Sm minus Sn. So this is for m greater than or equal to n. We will consider now for m greater than or equal to capital N. Then consider mod of Sm. And now when m is greater than or equal to n, this capital N, this value is less than 1, strictly less than 1, and we will write this as Sn as it is. So therefore this is less than or may be equal to, this is 1, it is less than 1 plus mod of Sn. Thus mod of Sm is less than 1 plus mod S capital M, and this is for m greater than or equal to n. Why we are doing like this or using these steps? Because we want to show Sn is bounded, and by definition of bounded sequence, when we say sequence is bounded, absolute value of every term of the sequence is less than a certain number, then the sequence is said to be bounded. And that means we have to show mod of Sm. The term may be denoted by Sn or Sm. Mod of Sm here we have denoted by Sm. So mod of Sm must be less than a certain fixed number, say capital P, for m belongs to I. So this must we have used there capital M, and capital M or capital P can be used. Mod of Sm is less than P, m belongs to I means for every value of m, I taking value 1, 2, 3, etc. all the terms of this sequence, absolute value of all the terms of this sequence is less than certain number, then the sequence is said to be bounded. So that we want to prove. Now what we have proved here, mod of Sm is less than this value, and this is a number, this is a positive number, 1 is positive number, and 1 plus mod Sn is again a positive number, and therefore that is a fixed number. But this happens for m greater than or equal to n, and we want m belongs to I for all m. So what are the exceptions here? That means this is true for m greater than or equal to capital M, and remaining terms we have to consider separately. What are the remaining terms in this? So here m takes values. See, m takes values 1, 2, 3 and so on. It will take value n minus 1, n plus 1 and up to infinity. So this result is true for these values n plus 1, etc. And the remaining are the result. We don't know what about the result, whether true or not, for these values 1, 2, 3 up to n minus 1. And for that purpose we shall consider like this. Let m be the maximum value. Let m is equal to maximum of these n minus 1 terms of the sequence. Maximum of, say, mod S1, mod of S2 and so on, mod of Sn minus 1. So these are n minus 1 terms, and m is the maximum value of these n minus 1 terms. Now we add m on the right side. Therefore, or then we have, now this mod of Sm will be strictly less than 1, or this 1 plus mod of Sn plus m. And now this is true for all m, and this is true for m belongs to I. Now you observe again, from S1 to Sn minus 1, all the terms are less than this capital M, because capital M is the maximum value. And from n onwards, the terms of the sequence are less than 1 plus mod Sn, and therefore all the terms will be certainly less than this expression. And this is a fixed number, fixed positive number, and therefore this shows that the sequence Sn is bounded. Absolute value of every term is less than a number, positive number, and therefore the sequence is bounded. So this shows that Sn is bounded. And this is what we wanted to prove, and hence the proof. So we have proved Sn is bounded, starting with the sequence is Cauchy sequence. Now we want to prove the converse of this earlier theorem, that what we have proved is, if a sequence is convergent, then it is Cauchy. Now we shall prove if a sequence is Cauchy sequence, then it is convergent, as our next theorem. If Sn is a Cauchy sequence, of real numbers. Then Sn is convergent. So for real number sequences, Cauchy and convergent are the same. Convergent implies Cauchy, Cauchy implies convergent. And the two definitions are important. All the definitions are important. We are using the definitions to prove the theorems. Now we shall make use of the earlier lemma. So what the earlier lemma says, if sequence Sn is Cauchy, then it is bounded. So Sn is Cauchy sequence. Let Sn be a Cauchy sequence. Therefore, by lemma, Sn is bounded. And because Sn is bounded, it has limit superior and limit inferior. Bounded sequences has limit superior and limit inferior. We have studied it earlier. We will make use of now the results from limit superior of a sequence and limit inferior of a sequence. Therefore, limit superior of Sn as n tends to infinity, and both must exist because the sequence is bounded, bounded above, bounded below, and limit inferior of Sn are finite real numbers and are finite real numbers, and that means they exist. Now if we want to show Sn is convergent. Now what is the condition for convergent sequences in terms of limit superior and limit inferior? We have studied earlier the relation. If limit superior is equal to limit inferior, then that is the limit of the sequence, and then the sequence becomes convergent. To prove Sn is Cauchy, we have to prove these two are equal. If limit superior is equal to limit inferior, that is the limit of the sequence, and the sequence becomes convergent. So to prove Sn is convergent, we have to prove limit superior of Sn is equal to limit inferior of Sn. And because this is finite, that is the limit of the sequence. So now to prove this equality, we have a relation. So this is earlier theorem, you may refer the theorem we have proved this. And now what is the relation between these two, limit inferior and limit superior? Limit inferior is the limit of the GLB of Sn plus 1 etc. And this is the limit of LUB of Sn plus 1 by definition. And therefore GLB is always less than or equal to LUB, and that means we have limit inferior of Sn is less than or equal to limit superior of Sn. We know that this is less than or equal to limit superior of Sn. And now, so this result is known result. Limit inferior is less than or equal to limit superior of sequence. But to hold the equality, what we have to prove? When we say A is equal to B, we have to prove the two relations separately. To hold A is equal to B, A is less than or equal to B, and B is also less than or equal to A. These two together will imply A is equal to B. So one part we know, limit inferior is less than or equal to limit superior. Now what we have to prove? limit superior is also less than or equal to limit inferior. So therefore we need to prove other part. That means this is also less than or equal to the left side expression. That is limit superior of Sn is less than or equal to limit inferior of Sn as n tends to infinity. So this is the relation that we want to prove, and we shall suppose this as 1. Now we again use the condition given in the theorem, Sn is Cauchy. Now Sn is Cauchy. Therefore, given epsilon greater than 0, there exists, by definition, there exists n belongs to I such that definition of Cauchy sequence Sm minus Sn is less than epsilon or mn greater than or equal to n. So we have applied the definition. The same condition, this is given, so we have used it. And now for this particular, we shall fix n, and that this will give, therefore Sn, we now select this m as n. Sn minus small sn is less than epsilon, and because this m is fixed, so there is no need to write condition for small m. Small m we have selected as capital M. This result is true for small m equal to capital N. So therefore we have replaced small m by capital N, and we kept only n varying. So therefore we have to write now only small n greater than or equal to capital M. You note this. And therefore what this will show further, this inequality will say that Sn minus epsilon, or instead of epsilon what we shall consider is this as epsilon by 2. So we can take epsilon as half epsilon, epsilon by 2, epsilon by 3, etc. We consider this as epsilon by 2, and therefore now this will imply Sn minus epsilon by 2 is less than Sn is less than Sn plus epsilon by 2, and this is true for n greater than or equal to n. By the condition for absolute value function, mod of a minus b is less than delta, we can write. So we have Sn minus epsilon by 2 is less than or equal to GLB of Sn plus 1, etc., Sn plus 2, and this is again less than or equal to LUB of Sn plus 1, etc., and this is less than or equal to Sn plus epsilon by 2. Now see, GLB and LUB lie between these two terms, Sn minus epsilon by 2 and Sn plus epsilon by 2. And the left term and the right term differ by epsilon. The difference of these two is epsilon. You may see Sn plus epsilon by 2 minus Sn minus epsilon by 2. So this is equal to epsilon. This cancels, and this epsilon by 2 plus of epsilon by 2 is epsilon. So therefore the left term and the right term of this inequality differ by epsilon. The left and the right, extreme left and extreme right term of this inequality differ by epsilon, and therefore we will have the difference of LUB and GLB is less than or equal to epsilon. Therefore, LUB of Sn plus 1, Sn plus 2, etc. minus difference of these two minus GLB of Sn plus 1, etc. is less than or equal to epsilon, because the difference of these two is epsilon. The difference between these two terms is epsilon. For example, if we have 5 is less than 7 is say less than 8 is less than 10. These are the terms, are less than or equal to. Now what is the difference between 5 and 10 and 5? That is 5 again, and therefore the difference of 8 and 7 is certainly less than 5. That is the meaning of this statement. And now we can consider this term on the right, and that means LUB of this Sn plus 1, etc. is less than or equal to epsilon. GLB we shall write first, minus becomes plus on that side, GLB of Sn plus 1 plus epsilon. And now we take the limit on both sides as n tends to infinity. Taking limit as n tends to infinity, so we get, now we know that the limit of LUB of this set is limit supremum. So limit supremum of Sn as n tends to infinity is less than or equal to, and limit of this is limit inferior of Sn as n tends to infinity plus epsilon. So this is the inequality we get. And now what we shall say is epsilon is arbitrary. Arbitrary means it can take any value, positive value, as small as we please, and therefore we can make this smaller and smaller, and then the inequality remains limit superior of Sn is less than or equal to limit inferior of Sn. But epsilon is arbitrary or arbitrarily small, and therefore we have limit superior of Sn as n tends to infinity is less than or equal to limit inferior of Sn as n tends to infinity, and this is what we wanted to prove. So this proves 1, and hence this proves the theorem. Because in this case limit superior of Sn is less than or equal to limit inferior of Sn, and the converse is also always true, limit inferior is less than or equal to limit superior, and thus these two are equal. And if the limit superior and limit inferior are equal, that is the limit of the sequence, and thus the sequence is convergent. So every Cauchy sequence is convergent. So this is the proof of the theorem. So remaining part we shall continue next time. Thank you.